Okay, now we are ready to move on to the multi-step synthesis. Sometimes it's called the total synthesis because we are using all kinds of known simple reactions to come up with a big molecule with so details in structure. So I think I mentioned it last time, you need to study simple reactions first. Those simple reactions with the simple molecules are tool for us to do multi-step synthesis. So each mechanism is considered as a methodology in order to create certain functional group, or in order to create certain geometry, certain stereochemistry, certain connectivity, and so on. So yeah, you choose SN2, for example, when you do, when you create certain stereochemistry. So when you run SN2, you can selectively get opposite configuration, right? If you do SN1, then you have chance to change the regio selectivity, by changing the connectivity, but you also get sometimes equal amount of the both stereoisomers, so it may not be your good choice. So these are the things that I mentioned before, and some methodology you adopt in your multi-step synthesis will be protecting some functional group, because simple methodology with a simple molecule may not work in the multi-step synthesis when you deal with a bigger molecule with a multi-functional groups and a lot of side chains attached to. So you plan for SN2, but even your small base on the primary carbon may not give you SN2. Then you come up with certain strategy by protecting something or activating some functional group or covering up or removing some bulky group for now, and something like that. And doing so, we often, almost every time, adopt retrosynthesis to think backward. In order to be effective in multi-step synthesis, it is required to change for you to study the reaction. So far, we've been focusing on changes of functional groups, such as a double bond going to the alcohol or alcohol to the carboxylic acid, things like that. But in order to make a bigger molecule, you need to connect. And obviously, we connected carbon and oxygen in SN2 or addition and so on. However, we mean more active connections, not only those nucleophilic ones, but carbons or anything. So we need to connect small pieces together in the control of selectivity of reaction, like a strong oxidation or weaker nucleophilic, or R configuration, or Markovnikov, or all kinds of things you should consider while you are making connections. That's what's required in multi-step synthesis. So change of the point of view is very much demanded here. Instead of knowing what SN2 is doing, sometimes you are asked to choose from the better choices. So say for changing something to some other functional group, you may think of substitution as one of the choices. But substitution can be done by nucleophile, as you all know, SN1, SN2. But it can be also done by radical. So in the carbon chain, you can substitute the hydrogen with the halogen, right? This is done by a radical intermediate. Also, substitution can be done electrophile. We didn't cover this yet, but say you can have the substitution like this can be substituted with the nitro group, and that's done by NO2 positive ion, not negative for nucleophilic SN1, SN2, not radical halogen substitution. It could be done with an electrophile. So you have all kinds of choices. Even addition, you've seen double bond turning into alcohol. This is done by electrophile and weak nucleophile. But if your double bond is this kind of double bond, then addition will be done by strong base, such as hydride, the one from ionic lithium aluminum hydride. This can basically add to the carbon. Then you'll need H plus ion in order to convert that to the alcohol. So you are making similar functional group, but depends on the situation you need to choose. And in the multi-step synthesis, you need to decide whether you want to go through the regular carbon double bonds, or you have to go through the carbon-oxygen carbonyl double bonds and so on. So initiated by electrophile for addition, initiated by nucleophile for the addition. Again, you have different choices. Even with this said, I'm not trying to say these are all the possible options for substitution or elimination. I'm trying to say now your mindset has to be not just knowing some few examples of typical reactions, but you should go by, let me find out what are the options learned from the given problems you have. Then you can freely choose from what option fit into your necessity from the analysis of the question. I know that's scary, but that's how things gonna be from now on. All right, now we're going from mechanism, studying simple typical mechanism of addition, elimination, substitution, and rearrangement as methodology for the multi-step synthesis. We still learn new mechanism, but let's spend more energy and time on functional group focused connection. So what do I mean by that? So you all know we learned that this unit as my popular example, but today I'm gonna use a methyl cyclohexane, but you can see that methyl cyclohexane has still this unit, right? So how do you react? What do you get? Only one reaction that brings you something out of this, if you remember, that was halogen, right? So how do you do it? Br2 with a light or heat, you can get there. Then from there, we learned that we can do substitution there and elimination there as well. And what do you substitute instead of the Br? A lot of things. So I can tell you, we can do these things, right? This is what I mean by functional group. Alkane can go to the alkyl halide, but then alkyl halide functional group is connected to be these functional group. You know how to eliminate and get the double bond, E2, E1, with a weak or strong bulky basis with the heating. And this as well, you can do SN1 and SN1 with water, and this one Br is gone, and instead you got this little triple bonded compound. So your nucleophile has to be this one, right? We know that the yield for the substitution may not be really great for this guy, especially when you look at the substrate, it is a tertiary. So you have a chance to get a pretty low yield, but for the sake of the concept, you can put this guy there instead of the Br in substitution, and you're connecting this functional group alkyl halide to the alkyne. So then, even ester, this alkyl group is on the oxygen, and the carbonyl group with the methyl group, that's ester. So you can create ester out of it. This is only a few examples of functional group here, but you can create a lot more variations with a different number of carbons on the product. Then we can even connect more. Let's try on this side of the double bond. You can connect all of these. Oh my God. Yes. So you can connect the alkane from the to the alkene. So if you ever need in your multi-step synthesis, you figure that I need to reduce the double bond, that's the situation. You do it with the hydrogen gas and the metal catalyst, right? You can connect the alkene to the alcohol and the other type of regioisomer alcohol, ester, alkyl halide on different carbon, epoxide, diol, you name it, you can connect. And that's not it, right? We can connect more. Voila. This alcohol, you can connect it to the carbonyl group, tosyl group, chlorine, ether, thiol, cyanide. I'm just running out of the room. And you can keep branching out. So that's what I mean by studying around the functional group connection. We've been studying on how to reduce it. What's the typical mechanism as the tool of a multi-step synthesis? You are studying one unit at a time. But now you still study mechanism, but you have to give your attention to connections with all those details I listed before, such as stereochemistry, regioselectivity, and stuff like that. Okay, let's try a couple examples. You attempt to make this one out of that in multi-step synthesis. This will be eventually used to make this one and further in total synthesis, for example. And for organic 1 students, this is doable. So why don't we try? Here you have alkane. So the simple reaction you remember is there's only one reaction you can do with that. You can put chlorine or bromine. We've been using bromine a lot, In this case, there's no selectivity, so let's just try chlorine. Let's put chlorine here. From here, you think, how do I connect from here to there? Well, I need the double bond. I need oxygen attached to it. So first thing I would say, if you think retrosynthetically, right? If I have this, then I can make that by oxidizing it. So you need some oxidation reagent. If you know any, try. One of the better one should be PCC as a weak oxidation reagent. You can oxidize alcohol to ketone. Then you are saying, how do I, get there from here? Looks far from here. And you are saying, okay, I can have OH if there is a leaving group there. And I have one. But if I use this out now, right, then replacing Cl with OH, then how do I make a double bond? So it's your decision, trying both out. See which one you like to do first. But I know that I should try to make the double bond first. So I should have something with a double bond already, then some leaving group, maybe chlorine, bromine, whatever. Okay, so you should have that. Then how do you get the double bond installed? We are planning to make the double bond with the chlorine. So let's make a double bond. Do you see it well? So you do elimination. You need E2, so something big enough, strong enough, and some help with the heat. And maybe solvent. You can give DMSO or something. DMSO is not really good solvent for a practical reaction, by the way. You can try acetone, same polar aprotic solvent with a low boiling point. But anyway, you can do E2. Then you can think of like, oh, let's put leaving group there. Well, you can try Br2 with the heat as a radical substitution, and the hydrogen from the allylic position, which is this position, is most reactive, because when you lose hydrogen here, the radical formed on this carbon will have a resonance with a double bond. Therefore, you will have most stable possible intermediate out of it. Then that carbon ion radical will react with the bromine molecule in the propagation step, and you get that as a product. Or you can use a chemical called NBS. This will also make you get there. Well, the NBS is actually N-bromo succinimide. It looks like this. It has a good leaving group portion with a bromine on it. So due to the, although it's not symmetrical like other radical initiator, with a multiple pi bond, this bond is easily broken in homolytic dissociation. So it generates small concentration of the Br radical, and that prefers not addition but the substitution. Okay, I don't want to get into that at the moment in detail, but yes. So you get there, and then making this to that is easy. You can use a simple SN2 with the OH minus and PCC. You get there. And again, it requires, even this question doesn't have anything like regioisomerism, Markovnikov, or any other details. It's just a simple connection of reagents. It's considered quite a simple version of the multi-step synthesis, but it requires a lot of thinking and strategy. There. In conclusion, from now on, when I present, I'm gonna focus on like connections more. So instead of giving mechanism focused instruction, I'll give you more like a synthetic instruction. Then I'll sidetrack to show a certain important mechanism. So if you understand what I'm trying to do, you'll be able to follow my talk better. So I hope this will make you get ready for the next stage, and I'll see you next time.